Thank you everyone for the questions. I guess considering the time and I need to kind of speed up with my presentation. So I think that the next the section I want to look at the PA design fundamentals on both active devices and passive network designs. So we start from the active devices, right? Let me first introduce the concept of Loadpull contours. As I mentioned, I want to cover more fundamentals. It is introduced to show that the PA behavior when and the PA is seeing a complex load, right? Not the simple ideal and the resisted, let's say ideal optimal load based on load line. And what if the load is mismatched, right? Let's look at the behavior. So let's take this class APA as an example. So let's assume that the real part of the mismatched complex load and the ZL and then basically is equals RL. The real part is RL, which is also smaller than R optimal. So therefore, in this case, the device will operate in the current limit regime without essentially pumping out the full current, but without reaching its maximum output voltage. The output power in this case can be calculated as 1/2 R optimal times Imax kind of square, and which is actually the K times smaller than the maximal and output power. The K equals RL divided by R optimal, which is smaller than 1. And here we can define the K as the power degradation factor. So for this particular and the current limit regime of the mismatched load, we can always add one reactance in series with RL. So therefore, the combination of the two will give us a higher load impedance. We can always increase the XL such that the drain RF voltage swing at the PA node will reach its maximum value of the VDD, right? The maximum reactance and the XL is now defined as, can be calculated as the square root of 1 minus K squared times R optimal, and before the whole load is reaching the maximum voltage swing and defined by the load line. Of course, in this case, the voltage current will not be in phase anymore because the load is complex, right? So anyhow, and for given RL and also the fixed power degradation factor K and the resulting RL plus JXL and the curve essentially follows a constant resistance circle on the Smith chart showing on the right. And on this trajectory, the PA generates the same output power with the same power degradation factor, right? Very similarly, we can look at the case when the load, real part of the load is actually larger than R optimal. And in this case, and the device is operating in the voltage limited regime in the sense that it achieves maximum output voltage, but without reaching the maximum output current. So similarly, we can put another kind of reactance in parallel and with it, and we can see that for the same output power for this and the same power degradation factor, that the impedance trajectory follows this the constant conductance circle on the Smith chart. Now, if we combine the two together, and this will form the full Loadpull contour with the same output power, with the same power degradation factor. And then we can plot this contour for different level of K and as a set of contours. This is essentially where the Loadpull contour is coming from. So now if the device output capacitance is excluded, right? For example, if we look at this load plane and the plane number 1, then the optimal load is real. Then ideally, the Loadpull contour should be symmetric between the inductive and the capacitive region of the Smith chart, right? So in this particular example, I have some numbers here. I will not go through the details. But if we look at the Loadpull contour 2, where we are outside of the device parallel and output capacitance in many cases, then the optimal load apparently should be inductive because the inductive part will resonate out with this capacitor. So the Loadpull contour will be rotated to the inductive half plane on the Smith chart. So an actual Loadpull contour for 45 nanometer CMOS SOI devices at 28 gigahertz is actually shown here on the right. The red curve is basically representing the 1 dB output power contour, where the blue curve represents the 5% of PAE contour. So we can also have other types of Loadpull contours, for example, for the PA linearity as well. But these are essentially large signal contours, and then we should choose the optimal load to fit the particular application needs. So next, it's important to understand the PA linearity distortions that are often described using both AM to AM and also AM to PM distortions. So if we have for example, a sine wave and input, right? We know that for a simple LTI system, linear time invariant system, the output will still be a sine wave, and just with a scaled amplitude and the altered phase, right? Which is and which can be completely described by this complex and transfer function and HS as at the fundamental frequency, right? And but for a nonlinear system with memory effect, for example, and if we only look at the fundamental terms, right, and the output signal will have many terms because of nonlinearity. But let's say we only look at the relevant fundamental terms and at the output and ignore all the other terms. The resulting output will still be a sine wave because we only look at that fundamental term. But the amplitude and the phase of the sine wave will change both depending on the fundamental frequency, omega 0, and also the amplitude of the input A. So therefore, we can see that these are nonlinear distortions now, both in the amplitude and also in the phase. So we can further show this in the IQ constellation plot. If we have AM to AM the distortion, which is actually gain compression or expansion, so and shown as a figure on the left. When we have AM to PM distortion, we will show this as a rotation of the constellation on the constellation plot shown on the right. Right, for example, for 10% of the amplitude AM to AM error, basically, and for and 1 dB AM to AM distortion contributes almost equally as, like, say, 6 degrees of AM to PM distortion. So therefore, we can see that the excellent PA design, we really need to have the balanced performance, balanced nonlinearity of both AM to AM and also AM to PM. Right. So at the same time, in reality, the AM to AM and the PM should be measured versus the output power, and an example and the measurement is shown here as the 28 gigahertz PA, and on the right, which is the AM to AM distortion, and registered as the OP1 dB is about 2.8 dB lower than the PSAT, and AM to PM distortion at OP1 dB is about 6.3 degrees, right? A very common performance. So both AM to AM and PM performance and will lead to the in-band distortions as the EVM degradation and of the transmitted and the constellation. So essentially, the constellation start to distort, right? And this is called in-band nonlinearity. And there's also another term called out-of-band nonlinearity or out-of-band distortion. And this essentially refers to the spectral regrowth and resulting in the adjacent channel and leakage ratio ACRR degradations. So the left figure shows the measured and the AM and the millimeter PA output at the lower average output power and with less linearity versus higher output power versus with higher nonlinearity and both at the for the same PA, right? We can see that essentially the tolerance on the in-band out-of-band the distortion based on the particular applications will eventually set the maximum modulated power a PA can deliver in practice. So, well, we may have where are the sources? Where are the sources of PA large signal nonlinearities, right? So if you look at the equivalent elements in a power device, most of them they are nonlinear. They contribute to the AM to AM and AM to PM distortions. So typically we can use Taylor and series and without memory or usable Taylor series with memory effect. So to model these nonlinearities. So next we can focus on several major nonlinearity mechanisms and see the popular techniques to mitigate them. Right. For example, the first one is called the transconductance nonlinearity. This is also called the GM nonlinearity. Is often the major reason for AM to AM distortions. The GM nonlinearity is biasing dependent. We know if we plot the linear term in GM and the second order term in GM2 and the third order term GM3 and versus the VGS, the biasing voltage, we can find that that the VGS and the biasing, we can find the particular VGS biasing where the GM3 is 0. Right? This is called sweet spot GM biasing. Right? And however, as we can see that this is probably only valid for small signal levels because this GM3 is around 0 only across the small signal range, which is typically not applicable for PAs. For large signal PAs, we want to expand this so-called 0 GM3 region to support large signal drive. We need to have some additional tricks, right? We notice that the GM3 and has the opposite sign above and below this GM3 optimal biasing point. So therefore, we can essentially have multiple devices putting them in parallel and bias the gate at different voltages, and then combine them together. So the total effective 0 GM3 will be held and over a wider power range. This is called multi-gated transistor techniques, MGTR technique. The schematic shown on the upper right with 4 transistors is an example. We can see that the simulated IMD3 and really shows that we'll have substantial reduction by using this MGTR technique. Okay, so for the AM to PM, the nonlinearity input capacitor CGS is often the major cause, and sometimes actually the output device and the output capacitance can be a reason. Sometimes the GM compression can also lead to AM to PM distortion, but in many cases, the input CGS and distortion is typically the major reason for the AM to PM distortions, right? So it is shown that the CGS nonlinearity can be actually canceled by using NMOS and the PMOS and the varactor or the transistors and in parallel, right? Because they have opposite the capacitive nonlinearities. Well, this will lead to an overall larger but flatter and input capacitance versus the input drive voltage, right? So the price to pay typically is the slightly lower gain and also a narrower bandwidth, but it will help us reduce the AM to PM distortions. Okay, so another major source of nonlinearity is actually the remixing of the signal order harmonics of the PA from the output and to the input. So we can see that actually many linear PAs operations will introduce substantial signal order harmonics. For example, the class B PAs. For example, the PAs with certain output waveform shaping, like class F inverse PAs. Right, this kind of signal order and harmonics can remix with the fundamental through the device nonlinearity, and this will result in the additional IMD3 components at the output, then both AM to AM and also AM to PM distortions. So there are different ways to suppress this signal harmonics, and we can have output filtering, input filtering, and also the source node filtering. Right, so we can see that typically applying these signal harmonic short circuits, we can really improve the IMD3 and the performance as well. If you are interested, please refer to these two example papers. They are talking about the details. Now, when we are talking about the higher frequency, and we need to consider additional effects, in particular the device gain and the device frequency. Right, this is really because the fundamental challenge for these high millimeter PA designs and the device gain is one of the biggest limitations, right? For example, for a 2-port active device, its small signal power gain can be expressed as follows, and in these equations, right? We know that for the lower frequency and probably until the stability inflection point, the stability factor K is actually less than 1, so the device is not unconditionally stable. Therefore, we have to use the definition of maximum stable gain as called MSG. And beyond this stability point, inflection point, and the device will be unconditionally stable, and we can use this expression of MAG and which cross basically, and eventually the MAG will cross the 0 dB and at the Fmax, right? This is where we define Fmax. So in reality, the device gain and the Fmax will highly depend on the device layout, the biasing, and also the matching. So the gain of the 40 Global Foundry 45 and the CMOS SOI process for the frequency is shown on the right. For the class A and the class B and the different biasing modes. So we can see that although the class AB may achieve actually a higher device drain efficiency and actually decreased Fmax from the 334 gigahertz and for the class A mode and to 262 gigahertz. As a result, we can see that the device level gain drops from 10 dB to 7.5 dB. I think this is probably really an example to show the questions previously was asked by the team lead regarding the device and the gain degradation for different biasing, especially at the higher frequency of operations. Okay, so the active device and the layout should also be carefully optimized to maximize the device and the FT and also Fmax for given technologies, right? So we can see that for given device FT, if we can minimize device for the CMOS device, we can minimize the gate resistance and the CGD, we can really improve the device Fmax, right? So in practice, if we can use a smaller and the device finger width with more number of fingers, will reduce this RG and improve the Fmax, right? But the upper and the right figure and shows the simulated Fmax and for a 45 nanometer CMOS SOI power device with different gate finger width. We can see that a smaller finger width will improve the Fmax, and the Fmax will be maximized as around 1 milliamp per micron of biasing current density, right? But more number of the fingers will eventually, we know, will increase other device parasitics such as gate distribution resistance and also the inductance. So there's really a limit about how small we can go in practice for the device finger width. So therefore, and we need to consider all of these things holistically. Typically, we need to have full EM simulation even at the device level to and also device parasitic extractions to really find the optimal configuration and for the particular application for the particular frequency of operation. Okay, so we know that the millimeter PAs often use the neutralization technique to cancel the device parasitic feedback, like CGD in the MOSFET, so to improve the gain and also stability. And a popular technique is to build this differential and amplifier and use cross-coupled capacitance. And here it's called CN. Right, the CN can provide feedback current with the opposite sign, and then therefore cancel the intrinsic CGD and the feedback. Right, this is what I want to mention, that this is also a broadband neutralization solution, and that can unilateral the device and boost the gain and enhance the stability. The resulting device gain is actually close to the Mason's and the device unilateral gain, and the U, which has a minus 20 dB per decay of behavior over frequency, and the gain versus the gain versus at the frequency of interest versus the neutralization capacitor can be plotted and for different neutralization capacitor values and shown at this volcano curve. And right, so typically the CN is chosen in the middle of this volcano curve just to make sure that the design robustness against the process variation. Right, so often people also use the MOS varactors as a CN so that they can better track the process variations. So on the other hand, neutralization will result in the very high input impedance that will actually make complicated your input matching, right? And also the parasitic inductance and the resistance of the neutralization capacitor will impact the neutralization, particularly at a higher frequency, because they will have their self-resonant frequency as well. So all of these should be carefully considered and extracted and by EM simulations and for these high frequency and the designs. So, well, next we can move to the design of the passive networks, right? So as a previous example, right, and if we assume that we want to build a single end PAs with VDD of 2.5 volt, knee voltage of 0.2 volt for 30 dBm output power, the optimal load will be 2.6 ohm. And this will require a 19 times and impedance transformation down from 50 ohm, right? This example really shows that the passive network design challenges because we don't have a lot of voltage swing for silicon devices. Therefore, we need to have smaller load resistance to generate high output power. Then we need to have high impedance transformation ratio or power combining. And all of these will lead to more loss and the bandwidth limitations, and make it even more difficult for commodity controls, and all of these need to be considered for the output matching network. Right. So let's look at several general approaches of output matching network. The first example is this L-match network. Right. For the upper left example, we will first place an inductor LP in parallel with load, and then put the capacitor in series. I think through the parallel to series conversion, we can see that how the impedance will be changed, and the LCS is defined and is designed so that it will resonate with LS, leaving the resistance and the resistive load, which equals R0 divided by 1 plus QP squared. Q is a quality factor of this LP and RP and R0. And similarly, there's this duality of the designs, which we will have placed the capacitor first and then inductor in series, right? The combination of these two is essentially the full set of this so-called L match. And we can plot both the networks on the Smith chart. We can see here that starting from 50 ohm, we first have an inductive parallel inductance and then series capacitance. We will land on this RL as example, 12.5 ohm. And similarly, if we first have a parallel capacitor and a series inductor, and we can get to the same value as well. So these two networks are duality with each other. Okay, so both of them are viable in practice. So one can also extend this concept and build a T-line based the mesh network for higher frequency operations, and we can use the equivalent and the impedance upcoming transformation network, and that can be built as well, right? So on the other hand, right, in many cases, one section of L match will have direct trade-off of impedance transformation, network Q value, bandwidth, and also passive efficiency. And for example, for large impedance transformation ratio, we will require a large network Q, and which will degrade the network passive efficiency and as well as the bandwidth. So we can show on this Smith chart, right, transforming 50 ohm to 5 ohm, the network value Q will be a factor of 3, which is much higher than the Q value we want to transform 50 ohm to 12.5 ohm, right? Well, the solution to reduce the Q is to use multi-section L match. As you can see that here, that we use 3-section L match, and we can get to the same value of RL equals 5 ohm from 50 ohm, but only with a maximum Q of the network of 1.07. That's a reduction of the Q. And but at the same time, we need to realize that it will require more complexity, more chip area, and more passive loss as a result. So nevertheless, and the multi-section network has been used and widely used, and also it can be extended to high-order reactive matchings. That is actually, yeah, very popular approach as well. So in the past several, I think 2 decades probably, the on-chip transformers have been widely used in RF and millimeter PA designs and circuit design, in particular for PA designs. There are different ways to model the on-chip transformers. I'm showing them here. Next, I really want to show that one of the major advantages of transformers for RF and millimeter PAs. Right, this schematic shows a very kind of simplified one stage and the PA network and PA and the power stage with input and output and a transformer based network. As we can see that at the PA output, the transformer will act as a baton with a differential to single-ended conversion. So that's the advantage and use of the transformer. It can also combine the power from the 2 differential branches. That's why the phase and amplitude matching of them is very important, so that we can have efficient combining. It also can perform the built-in impedance transformation as well, depending on how we design the transformer. That's another advantage. Moreover, the primary side of the transformer is typically connected with the differential PA. So therefore, we can use the center tap to allow the VDD and DC feeding without using any RF chokes. This improves the performance, frequency performance. This also reduces the chip area required. We can actually add additional filtering network at the center tap to provide even order harmonic controls, which will be useful for PAs such as class F, F inverse, or class J PAs, right? Or to provide the linearity improvement as a signal harmonic short, as we just mentioned earlier as well. Now with the baton operation and the transformer can naturally enable differential PAs that will allow the capacity neutralization. That's another advantage of using this differential and transformer-based PAs. And the neutralization will be broadband gain enhancement as well as stability improvement. At the input, we can also use transformer to couple this PA, right? We can use a differential transformer that essentially will block the common mode signal propagation between the stages. This improves the stability and as well. It also does the input matching too, and depending how we design this transformer, right? And one more thing which is very important is that with this transformer, we can use the center tap of the transformer to bias the gate and or base of the PA device without using any large biasing resistors. Then the biasing network will have a very small and time constant with low memory effect. This will enable gigahertz very fast dynamic biasing, and which are critical for millimeter PA and 5G designs too. So here is an example of how to design a practical designs as an output matching network for millimeter PA at 28 gigahertz. I will not go through all the details, but you can see that, and this transformer essentially achieves all these functionalities just within using one transformer, and it can achieve all of these and essentially in a very compact form factor too. Yeah. To further boost the PA output power, and we know that in many cases impedance transformation is not enough. We have to have some kind of power combining, right? We just have to combine the output power from multiple PA devices, right? So and typically the different power combining techniques can be divided into 3 categories, right? The first one is the direct parallel power combining, for example, right? We call it, sometimes it's being called zero phase power combining, but they are all the same thing. So it is simple and compact, and but typically it does not offer a lot of isolations among the amplifiers, right? So that's the advantage and also disadvantage. The signal type is this kind of distributed power combiners, and we can use the Wilkinson power combiners, we can use the Gizo power combiners, for example, and we can also use quadruple power combiners. So they typically support good isolations, and among the stages. They can also provide asymmetric power combining as well, but they are often very bulky and can be bandwidth limited as well. And the third type is actually this transformer-based power combining, and they can be compact in the broadband with impedance transformation. They can also support many implementation variations that we'll discuss next. Okay, so if we use transformers, and we can enable both series and parallel power combiners, right? Shown on the left, this is the series power combining and transformer. Essentially, it will add up all the output voltages from different PAs together in a coherent fashion in a signaling term, so that the NPA branches will effectively combine in series, which enables a natural downscaling of the load impedance for each PA. That, as we can see, that is very useful for high power PAs. In parallel, we can also perform parallel power combining, and by adding up all the output current of the PAs in this configuration shown on the right. So in this case, the N and the PA branches are effectively combining parallel, which enables a natural upscaling of the PA load impedance, right? So in this case, as a circuit duality. So in addition, right, and there have been the research work on using this hybrid series and parallel power combining to really achieve the optimal and the performance for the power combining, and this has been reported as well. So in addition, the transformers can be used to build broadband and high order matching network for wideband PAs, and I'm showing 2 popular examples. The one on the left is to use transformer network to realize the bandpass ladder-based filters, which while the one on the right essentially use transformers to realize a coupler and a coupled resonator and the filter and the architectures. We don't have time to go through all the design details here, but I'm showing all the network transformation and the steps, and just for your reference, right? And the important thing is that both networks, the one on the left and also the one on the right, can realize impedance transformation over a very wide bandwidth, because their network prototypes are wideband, and therefore they are very useful for broadband PAs. And also both examples can be cascaded to achieve high order networks to further extend the bandwidth, right? Okay, so for the passive network, I think there was a previous question regarding the distributed network versus lumped network. Indeed, this is a very important discussions. When we move to higher millimeter frequencies, the lumped transformer network designs are typically more restricted, and because they have limited self-resonant frequency, the lumped transformer should be, we have to design it to be very, very small with narrow traces, and to achieve and to ensure high self-resonant frequency, then we can still use them as a transformers. But in those cases, they will be very sensitive to parasitics. They will be also very sensitive to the routings, and they will actually also have low coupling as well. The on-chip and the coupled lines balance and for these high frequencies are becoming a very popular choice, and with very versatile designs and at higher frequencies, for example, 140 gigahertz and above. So a generic coupled coupler balun is shown on the left, and the port 2 and the port 3 are the differential ports, and the port 1 and essentially the single and the load. As we can see that, because the coupler balun typically will have some kind of intrinsic symmetry, then we can use even mode or an odd mode analysis to understand the impedance transformation and also the bandwidth of the couplers. So an example coupler balun is shown here, and with vertical coupling of 2 metal layers, very common in this using CMOS process, a silicon process. So with a compact footprint, we can see very compact. It achieves a wideband low loss operation from 90 gigahertz all the way to 180 gigahertz, just using one coupler and in a very compact footprint. The amplitude also phase balancing and excellent over this 70 to 190 gigahertz. Right, that's the advantage of using couplers. Right. So to summarize the coupler balun properties, it offers low loss and broad bandwidth, as we can see. It can naturally absorb PA and the device output capacitance for very compact designs, and they actually also ensure high common mode rejection and almost zero even mode transmission. This is a big advantage. This guarantees the balancing of the differential impedance and also in phase differential signal propagation, because it will block any common mode signals going to the output. It will also offer the built-in impedance transformation and also many other design and variants and properties. Right. For example, and in our previous paper, we have shown that the coupler balun can be used to realize impedance inverting or scaling. It can be found that this behavior, impedance inverting or scaling behavior, really depends on the phase of S21 if we define the ports like in this way of the coupler balun. If the phase is around plus minus 90 degrees, the network behaves as an impedance inverter balun. So when the load increases, the driving impedance actually decreases. Okay, if the phase is 0 to or 180, it is scaling balun. Essentially, the driving impedance, differential driving impedance, will scale and together with the load impedance. These properties will be very useful to build advanced PAs, such as Doherty PAs or out-phasing PAs at the higher millimeter frequency. So moreover, the coupler baluns can be cascaded, can serve as a series power combiner to further boost the output power, and I will show you as one of the design examples later. Okay, I think this concludes the signal part of the presentation. So if there are any questions, I can happy to answer.
Okay, hi, I see Kevin. I'm asking you to unmute. Please unmute yourself.
Yes. Hi, Professor Wang. So thanks a lot for very informative talking. So I have two general questions. So one is for the millimeter wave PA, usually we need multiple states because each state has limited gain. So is there any strategy on the power supply and ground for each stage? Let's see, do we need to separate the power supply and ground for the driver and the last stage? So that's the first question. And the second question, and you just mentioned the distributed coupler balun. So at what particular frequency we should choose the distributed design instead of the lumped transformer?
Okay, that's thank you for the question. So first of all, I think it's kind of common practice that we want to separate the supply voltage for the driver and also the PA. At least we want to ensure a very good bypass between the two. This is really for the conservation of the stability, because we don't want to have any feed through and feedback through the supply lines. That's the main consideration. However, as I know that in many actually the product level designs, sometimes having separate supply lines is not feasible. Then in that case, you need to really carefully model that supply lines and also bypass and adding to it. That's important. To address your signal question, to what frequency we should consider using this the cassette coupled balun? Well, I would like to say that this is useful for higher frequency. The higher the frequency you go, it will be more useful compared to the transformer. It's probably hard to make exactly what is the cutoff line. But as I will show you later, this technique can be used very nicely for 60 GHz PAs to have efficient and in-phase power combining and form a kind of the DAT structures. I'll show you later.
Okay, good.
I hope that answers your question.
Okay.
Yeah, thank you.
Thank you.
Okay. The next one, Lily, please unmute yourself.
Yeah. Thank you, Professor Wang. I have a question on the power combiner. So you mentioned that some combiners not isolated. So I'm curious in which scenarios the isolation can be an issue, because for transistor itself is unilateral, meaning the S21 is much bigger than S12. So I'm just curious when the isolation can be an issue in terms of the PA design.
Yeah, so here the isolation, I'm not talking about S21 or S12 kind of input-output isolation. I'm talking about the isolation between the ports. Okay, this is a particular issue if the PA you are designing, has a tendency that some of the branches may fail during the operation, or you want to design the PA with a very high reliability that even some of the branches will fail, other branches should operate and still the same and with high reliability. Then you need to choose the combiner topologies where that will give you better isolations.
Okay, I see. Yeah, thank you.
Next question, Sarah. Please unmute yourself, Sarah.
Hello, Professor, and forgive my voice because it's just 5 here in Zurich. I wanted to ask you one question about the load pull measurements for device characterization as like a device characterization point of view as a device designer. I wanted to ask you that how is the input power, like for example, the single tone continuous wave is going.
Oh, okay, so I guess your question is about
affect our P out, like that we are going to.
I think your voice is a little bit breaking up. So
Sarah, we missed the last part of your question. Can you repeat?
So my question is about the load pull characterization of the devices from a device design point of view. When we are doing only like single tone measurements, is that going to affect our gamma L? Like if, like for example, the input power is only a single tone. And also one more question is about like the level of the P-in when we are actually considering our best or our optimum gamma L. So like at different P-ins. So for example, at P-in -1 dB or like 6 dB back off, our gamma L is going to be different. So what will be like the best way to consider the optimum gamma L?
Oh, that's a very good question, and I think that you have a good experience on the device level characterization, I'm sure. So this really depends on application, right? So in many cases, when we start a design, we have to start from somewhere, and then we actually often use the single tone as the stimulation as the excitation source, so that we can define and find the optimum gamma L, right? And but eventually, I think in many of the application design practice, later on you want to polish the PA. Often you may also want to even use the modulated tones to do that. And then going back to your question regarding whether we should use what is the level of the input signal we should use to find the gamma L. Totally, it really depends on the input, right? So again, this goes back to what kind of PA you are designing, right? So if you are designing normal class A BPA and then the input voltage or power level also depends on what kind of driver you can have and the breakdown of the driver and the supply voltage driver limitations too. So with that consideration, you can kind of more or less understand what is the maximum input voltage drive. And based on that, you can you can design input drive, and then you can design the gamma L, optimum gamma L. Now, but for other type of PAs, for example, Doherty PAs, and the main PA should operate at the 6 dB power backoff by itself, and before any active load modulation is being turned on. So in that case, you should use actually backed off and the input drive, so that we can find the optimal and the gamma L. So for in those backoff case, so I think it depends on the applications. Yeah. But for the basic practice, class A BPAs, as a starting point, I think you can certainly use the continuous wave and let's say around the input 1 dB or 1 dB compression point and the input drive to find your starting point of the gamma L, and then start your optimization from there.
Okay. Next question, Fabio. Please unmute yourself.
Professor Wang, a consideration about how we measure stability. Now, in the slide that you presented, it was measured with K. Of course, it can be also the mu. They're interchangeable. But is that enough for power amplifiers? Because as far as I'm aware, K or mu parameters, either one or two, are of course indeed necessary conditions for stability, but not sufficient. For example, we might need to add another one like the determinant, for example, S11, S22 minus S21, S12. Is this relevant, or it is enough?
It is very relevant, and I see, I think you raise a very good point. I kind of purposely don't want to go to the details here, and okay. So for the stability calculation, it depends on for the actual, you know, we should talk about theory. We should also talk about the practice, right? So the theory that yes, and you know, and you can use the stability factor and the K or and the mu. But these are, in reality, they are all small signal estimation and small signal characterization of stability, right? The PA is actually a large signal thing. During the large signal driving, its biasing is changing and constantly and through your driving. So therefore, and in many cases, we also need to model the large signal stability of the PA too, right? So there are actually, you know, essentially you need to, there are different type of way to test the PA stability for the large signals. So I think in the practical designs, that's actually probably even more important than checking the small signal stability. Yeah.
Thanks, Professor.
Yeah, thanks.
Okay, next one is Yilong Zhao.
Hi, Professor Wang. Yeah, thank you for your presentation. My question is in terms of the balun design, especially the coupler balun. I think it's most suitable for like CMOS technology, right? Because for gallium nitride, usually they're just like two metal layer that we can access for, is at least for UMS or WIN semiconductor, they just have two layers of metal. And why is the common ground? So it seems it's very hard to design the transformer using GaN technology. Yeah.
And that's a very good point. And we also have some successful and unsuccessful experience and porting this topology to different process. It really depends on the backend option you have for particular technologies, right? So I can say that okay. But we can do this in indium phosphide technologies because it does give us enough metal layers. For the GaN process, it depends. And as you said, yeah, if you only have two metal layers and one's ground, and it's probably hard to use. Well, maybe you can choose to use, and for example, as basically the edge coupling, but then the coupling coefficient will be limited. Your design freedom will be limited, right? So yeah, it depends on the really depends on the process.
Okay, Sushil Kumar. I think you are unmuted. You can speak. Okay, let's go to next one. Yes, Sheer, please unmute yourself.
Hello, Professor Wang. My question is regarding the when you were talking about the voltage limited and current limited at the drain terminal, where both the current and voltages were in both scenarios not in phase. So are there any techniques to make them in phase? Because inherently, if they are in phase, we will get maximum power out of the transistor, obviously. If they come in phase.
Certainly. Here I'm talking about the cases when they are not in phase, when you have mismatched load, and also you have additional reactance. This will, I mean, just by circuit theory, if your load is not in the real, and they will have mismatched phase, right? So I'm not talking. I'm not here referring to a desired design case. This is actually the cases to analyze the load mismatch conditions.
Okay.
In reality, yeah, in the actual designs, we always want try to make sure they align in the same phase, as you mentioned, so that we can have optimal output power and also efficiency, for sure. Okay.
Okay, Sushil Kumar, can you unmute again? I think you're unmuted. Can you speak? Maybe you have a problem with the microphone. All right, I guess we can move on, Professor, and we can probably have one more quick Q&A at the end.
Yeah, sure. And considering the time, I think that probably should, I prefer to finish my presentation, then we can ask the question maybe at the end of my talk. Yeah,
please go.
Right. So, okay, next I want to show you, and we have